start. We have one speaker this afternoon, Bloch. It's going to talk to us about optimal control, integrable systems, and discrete dynamics. Please, Tom.
Well, thank you very much. Thanks for the invitation to be here. It's very nice to be at the Newton Institute again and in this program. So what I'd like to talk about today are some connections between the three things in the title here: optimal control, integrable systems, and discrete dynamics, which includes a little bit of integrable discrete dynamics. So this is a survey to some extent, and also some new material that we've been looking at that links these topics. So the idea is we're interested in certain kinds of optimal control problems, certainly that have a sort of geometric flavor, particularly what are called kinematic optimal control problems that arise in such things as rigid body control. And so one can ask a number of questions, of course, about an optimal control problem, how you can solve them. And in general, of course, optimal control systems like general ODEs are not solvable in general, but sometimes they are solvable and they give rise to some classical integrable systems that we know how to solve. So that's one of the interesting things, and they often give you new ways of formulating these integrable systems and give you ideas how to integrate them. But actually, we were also able to find some new integrable systems which generalize some of the classical integrable systems, such as the geodesic flow on the ellipsoid, for example, and certain flows on Stiefel manifolds. So using this sort of optimal control formulation, you can sometimes come up both with these new ideas on how to formulate integrable systems and nice ways of formulating them and solving them. So the work I'm going to talk about today is mainly sort of recent work with François-Gay Balmaz and Toda, that reflects some earlier work with some of the other people that I mentioned there. What I'm going to do is start with a sort of representative example, the so-called symmetric rigid body equations, which goes back, in fact, to some work I did with Jerry Marsden. So I'll look at this in the discrete and smooth setting, and that will sort of provide a sort of template for the rest of the talk. The general problem is what we call the Clebsch problem, which is a sort of kinematic problem on a Lie group, which has a nice sort of general formulation that includes many of these others. And here, in this third point, I mentioned some of these classical integrable systems that are famously solvable. For example, the Jacobi flow on the ellipsoid. Of course, that goes back to Jacobi in 3 dimensions, but it turns out to be a solvable system in higher dimensions as well. And for example, the flow on Stiefel manifold, which basically is a flow on matrices which are not symmetric, includes some of these other cases that I mentioned. For example, the flow on the ellipsoid at one end and the rigid body on the other. And it turns out that there are a host of sort of similar systems in between that are solvable. And there's some other interesting systems that also fit into this context, such as the flow on symmetric matrices, which I looked at with Aria, the Toda flows, which is another classic set of integrable systems, and the flows due to Moser, which are related to instrumentally algebraic geometry, the geometry of quadrics. So I'll mention that just briefly, and one of the things we're working on right now is how to fit it into this general formulation. So one of the things one's interested in an integrable system is writing the system as a so-called lattice pair, and if you can do that, very often you can integrate it. Moser came up with a rather large class of systems that you can write like that, and it turns out that many of the so-called low-rank systems that we look at here fit into that setting. Okay, so here is just a little dictionary of something of what the flows look like. So at the top there I put the generalized rigid body equations. So this is just a standard Lie bracket, so m dot equals m bracket omega is m omega minus omega n. And I'll come back to this, but this is just a generalization of the three-dimensional rigid body flow. M here is the momentum matrix, which is related to the angular velocity matrix by m equals lambda omega plus omega lambda. So this is an integrable system. You can rewrite it also as what I call the symmetric rigid body equations, which actually came originally from the optimal control picture, and I'll come back to those in a moment. And here are two pairs of flows that are interesting, but slightly different from the rigid body flows. First of all, there's the Toda flow. So the Toda flow is a famous integrable system. It originates actually in looking at particles on the line interacting under an exponential potential. Flaschke found this wonderful transformation to a symmetric tridiagonal matrix, And that enables you to write it in this kind of lattice pair form that I've written here, x dot equals x comma pi s of x. So in the original form, x is a tridiagonal symmetric matrix, and pi s is its skew symmetric part. So that means you simply just cut out the diagonal and replace the lower first diagonal by its minus. And that turns out to be a very nice way of capturing the integrals and showing it's integrable. It also turns out to have a nice gradient structure. You can rewrite it in this double bracket form, which is a fun thing to think about, something else that I looked at with Aria for a while. And this is a really beautiful thing for writing down integrable, so-called gradient systems. And that's related to something called the normal metric, which I'll also allude to in the talk that we go along. So it's a metric flow with respect to a very particular metric, and it has this very nice characteristic that the flow both has a Hamiltonian type form, the first equation over there, and a gradient-like form. And then there are these symmetric flows, which take the form x dot equals x squared bracket n. And again, you can formulate them in an optimal control way, which wasn't that obvious when we first looked at it. And you can do all sorts of interesting things with it, including integrating it and writing it in discrete form. And I'll show you some of the discretizations of these systems as well. So here is first of all, the rigid body equation. So the first picture there is just the classic rigid body phase portrait on the momentum sphere. So if you look at the three-dimensional rigid body, it evolves on a momentum sphere. The total momentum, m1 squared plus m2 squared plus m3 squared is constant. And you get these trajectories on the momentum sphere, two elliptical fixed points, which are stable, and one hyperbolic fixed point, which is unstable. So the Euler equations are what describe these, the dynamics in the angular velocity. So it's just I omega dot equals I omega cross omega. I here is the moment of inertia, and omega the vector of angular velocities in the body frame. And if you want to see how the system rotates, you also add the kinematics. So theta dot equals theta omega hat, where omega hat is the so-called hat map. It maps the vector in R3 to a matrix in little SO3. And these equations are also sort of famously integrable and very nice in lots of different ways. So as I did here, it evolves on this momentum sphere, where mi is I omega I. And these equations can also be written in so-called Euler-Poincare or Hamiltonian form, in the form m dot equals m cross omega. And the Hamiltonian is basically the pairing between m, the momentum, and the angular velocity. And it has enough integrals. So, and I'll come back to this. So for an integrable system, basically, if you're on a 2n dimensional symplectic space, or vector space, you need n integrals. In this case, it's a 3-dimensional system, so it's Euler-Poincare rather than Hamiltonian, but you've got plenty of integrals. You've got two of them, the momentum squared, if you like, and the Hamiltonian, and that's enough to show it's integrable. So the interesting generalization, which goes back to Manakov and then Mashenko and Fomenko, is the rigid body on little SON, although in fact it generalizes to any reasonable Lie group, in particular compact Lie groups. So in this case, what you do essentially is you replace the cross product by a matrix bracket. That's essentially it. So you use a pairing on SON, the trace pairing between two elements of the Lie algebra little SON. And if you think of the cross product as being replaced by the bracket, you get these equations here. So q dot equals q omega, that's again the kinematics. It tells you how the rotation in space is related to the angular velocity. And the angular velocity evolves according to m dot equals m bracket omega. And again, this is just m omega minus omega m. And m is related to omega by this little transformation that I showed you earlier, lambda omega plus omega lambda, where you can think of lambda as a diagonal matrix, and it represents the mode of inertia. So that's not quite a bracket, but it's a positive, definite operator on the spaces of omegas. And the beautiful thing about this is writing in this way is what enables you to show that the system is integrable. So so J here is the symmetric positive definite operator, lambda is its diagonal matrix, and if you go back to the R3 case, you can relate the lambda i's and lambda j's to the J of the standard inertia operator. And as I said, this goes for any semi-simple Lie group, and you can show the system is integrable on SON and, in fact, any semi-simple Lie group. And that goes back to Mashenko and Fomenko, and I'll come back to that. So before I talk about the integrability, though, I want to say something about its relationship to optimal control and discrete dynamics. So firstly, that there's a right invariant counterpart. This was the left invariant form. You can just flip things around. So I can write it as Q equals omega QR dot, if you like, equals omega R QR, and the bracket flips its sign. So that's not too important, but it sort of, that natural symmetry occurs in the optimal control setting. And so you can relate them rather nicely by this little lemma over here. Another thing you can do with them is rewrite them in the following way, and this makes a nice connection with optimal control. So these are the so-called left invariant symmetric rigid body equations. So symmetric in the sense that those two equations look the same. So instead of having a bracket for the second equation, I have a second equation which looks like the first equation, just in this new variable p, and that p, for those of you who do optimal control, is just the adjoint variable from optimal control. So we use that variable for good reason. So it's also a momentum variable, but not the same momentum variable as the momentum m that occurs naturally in the Euler equations. So these look linear, but of course it's not a linear system, and indeed it isn't. So omega here is a function of q and p. Omega is given by j to the minus 1 of m, where m is equal to q transpose p minus p transpose q. So in fact they're cubic equations in qp, and they depend also on this inertia operator j. And what you can show is that if q and p is a solution of these symmetric rigid body equations, then qm, where m is just q transpose p minus p transpose q, satisfy the rigid body equations that I showed you earlier. So that's just a computation, actually. It's a fun computation. So I do the absolutely obvious thing. I just put m equals q transpose p minus p transpose q, and I differentiate it using the product rule. And so I get q dot transpose p plus q transpose p dot. Substitute those equations in, and you get m dot equals m bracket omega. So those equations exactly recover the original rigid body equations. Yeah.
And are they Clebsch variables for the?
Yeah, they are. Yeah, that's essentially what they are. That's right. So another just interesting observation, there are all these conservation laws floating around, and you can check, in fact, that the spatial angular momentum is given by this little m, which is pq transpose minus qp transpose. So that's as opposed to q transpose p minus p transpose q. So again, it has that rather nice symmetry. Now, of course, so you wonder exactly how equivalent they can be, and this is an important point because, of course, the rigid body equations evolve on the tangent space or the cotangent space of SON. So it's T star SON. The equations that I just wrote down for you are equations on the group. So Q and P are both in the group SON. They have this sort of symmetry about them. So they can't be exactly the same, but it turns out they're almost the same up to level sets. So you can go from one to the other. So if I differentiate M, as I said, Q transpose P minus P transpose Q, I get the rigid body equations, and you ask if you can go back. So can I extract out of the M equation the P equation? And it turns out you can do that in a rather nice way. So if you let C denote the set of Q and P's that map to M's with operator norm less than 2, and S denote the set strictly less than 2, then it turns out as long as the operator norm is strictly less than 2, then you can actually solve. So if a norm M op less than 2, you have a solution. You can actually compute P in terms of Q, and it has this rather pretty formula here, P equals Q, e to the sig to the minus 1 M over 2. So there's this algebraic formula which takes you from one to another, and it's completely exact and general. The only thing is you have to do it on level sets of M, so to speak, these level sets M equals 2. So you can't do it globally, but locally, and at least in a large set, this map goes back and forth. It's one-to-one. So that's a rather nice thing about them. And this is just a computation. So on the face of it, you needn't know anything about optimal control or integrability or anything. It's just a little bit of algebra. That's all that is. And then again, just like the classical rigid body equations, there's a sort of right invariant form of this as well. just put everything on the right instead of the left. And it has a Hamiltonian form, so so the rigid body equations, of course, are Hamiltonian. They're Hamiltonian in general on T star SON, or whatever Lie group you're looking at. It has this cotangent bundle symplectic structure. You could ask how these equations, the symmetric ones that I've just written for you, are Hamiltonian. And it turns out they're Hamiltonian, well, they're in various ways, actually. Of course, you can reduce it in some sense, just in the way I showed you to the classical case. But they're in fact Hamiltonian in a larger sense on the space in which they're embedded. So you can think of this all as matrix problems, and the matrices in big SON, just the orthogonal group, embeds in n by n matrices. And so if I just think of the symplectic vector space GLN cross GLN, n by n matrices crossed with itself, it has a natural symplectic structure, and you could write down this Hamiltonian over here, which is quartic, and you can check that just using the standard symplectic structure, it gives you these rigid body equations. And the quartic is natural, since the equations are cubic. And on top of that, it leads, as one hopes it would, SON cross SON invariant. So it stays on SON. Yeah.
What do you mean by natural? In which sense is this symplectic structure natural?
Right. Well, so if I have any vector space, I can just take its dual. So I take the vector space with its dual, and there's a natural pairing between the variables q and the variables p on the dual space. So it's
and this turns out to be exactly the trace.
Exactly. Yeah, that's it. So you can think of the dual space as identifying the space with itself by the trace. That's exactly right. Yeah. So that's the flow, and that Hamiltonian is of course equivalent to the original Hamiltonian, the rigid body equations. So so now let me say something about how you relate this to optimal control. So just to remind you, so optimal control problems, you not only have the variables for the system, so-called state space variables, but you also have a bunch of controls which are supposed to steer you around, right? So the standard so-called affine nonlinear control problem looks like this one over here. I have x dot equals f of s plus sigma gi ui. So the f is sometimes called the drift vector field, because that's what happens if you turn off the controls, you just drift along, and that's the sort of natural intrinsic dynamics to the system. And then the g's are the control vector fields, and they're the things that sort of steer you around. When f is equal to 0, we say the system is kinematic. So that often plays a big role in control theory. So one looks at the dynamic case, which is the full thing, and the kinematic case. The kinematic case, as the name suggests, means you don't really have a sort of natural dynamics. There's no f, it's just the controls. And that's, if you like, people often think about it as moving the system, well, you can think of it in two ways, as moving the system slowly. So you're moving it without dynamics, so you're sort of rolling a ball, say, around between a bunch of obstacles without caring about the intrinsic dynamics of the ball. So you say just pushing it around. And you can also think of it as direct control over the velocities of the system, because if you get rid of the f, that gets rid of the dynamics, and it's just a first order system, x dot equals sigma gi ui, so you have direct control over the velocities. And that's what happens sort of basically when you push a ball around with your hand. So that's the control problem. The typical optimal control problem is you want to minimize, say over u, the integral 0 to t, some cost functional g of x u dt. You can generalize that in various ways, but that's sort of the standard thing. And so you want to optimize this thing, and it's subject to a couple of conditions. First of all, the differential equation constraint, x dot equals f of xu. There's a state space constraint, x is in the manifold M, and there's a constraint on the control. So u lies in some class of control. So usually that's quite broad. U1 allows for things like bang-bang controls. It needn't be smooth, for example. It's some set. And sometimes the controls are bounded, sometimes they're not. The easy case is the bounded case, where you can take things off to infinity, but you can't always, obviously, and certainly not in real life. And then there are endpoint conditions. So you start off at some point x0 and you end up some other point. And that's, of course, the big difference between optimal control and ODEs, is that that they're endpoint conditions. You know where you start and where you end, as opposed to just having an initial value problem. So how do you solve an optimal control problem? Well, that's a big subject, but one of the things is the so-called Pontryagin maximum principle. And so then it's just really, if you like, constrained optimization. And what you do is you have the cost function g. You have some sort of nominal multiplier p0 which multiplies g, and then there's an adjoint variable p, which is paired with u. So basically what you're doing is exactly what I said earlier. You're minimizing the cost subject to the constraint of x dot equals f of x u. And the way it basically works is you take that Hamiltonian, you maximize it subject to the constraints that I mentioned. So I maximize the Hamiltonian with respect to u. Once I maximize the Hamiltonian with respect to u, I end up with a Hamiltonian that depends only on x and p. And so at that point, you would have a regular Hamiltonian function, and I can look at the dynamics. So that's the maximum principle. And it's actually very general. The nice thing about the maximum principle is you can use it for all sorts of pretty non-smooth and interesting systems. I'm not going to worry too much about most of its generalities, but it's a rather amazing principle. And in some sense, it includes Hamiltonian dynamics, as you can see. So that's what Hector Sussman always used to say, that really the Pontryagin maximum principle is more general than Hamiltonian systems. Optimal control is, so it includes it in this nice way. And then you can wonder, so once you've got this, as I said, you can wonder about integrability. You can ask, well, can I solve it or not? And since this is a Hamiltonian system, it doesn't really matter where the Hamiltonian system came from. It could be the original Hamiltonian system you had from some dynamical problem, or you could be looking at the Hamiltonian system that arose from some optimal control problem, and you can wonder if it's solvable or not. But in either case, you can apply the famous Arnold-Liouville theorem that says for a system on a 2n dimensional symplectic manifold, in other words, you can write down Hamiltonian dynamics, the system is integrable basically if there exist n everywhere independent integrals, or almost everywhere independent integrals on n, which are an involution, and that means they commute with one another under the Poisson bracket. So you have these, you simply have to have enough commuting integrals, and you can solve the system in principle. Actually solving it in practice is actually tougher, and that's where writing down the lax pair, for example, the bracket form helps. So there's a whole sort of story about when you can, when you can do it in principle and when you can do it practically. So now let me sort of circle back and relate this to the rigid body equations. So now I'm going to look at a particular kinematic optimal control problem. So I want to minimize over a bunch of controls u, the function u comma ju, where u is in the Lie algebra, little son. I can think of it as controls, if you like, for the rigid body. And the constraints in this case are just the kinematic dynamics. So I have q dot equals qu. So q again is son, and the rotation. And so this is, you can think of it as the kinematics. This is really what I wrote as q dot equals q omega before. So omega you can think of really as angular velocity, if you like. Then I have these two endpoint conditions, and I just do the Pontryagin maximum principle. So I simply write h equals p comma qu. I have the cost function u comma ju, and the optimal controls. So you do exactly what I mentioned earlier. You minimize this with respect to u. You find an expression for u. U is equal to that quantity over there. And if I just substitute u into those two equations, I get the cubic rigid body equations. So that's how it pops out. And so I sort of gave it to you backwards from the way we found this. So the way we originally found the symmetric form of the rigid body equation is exactly this. We did this computation, and then we noticed, of course, that you could do what I did earlier. You don't really have to know this. You could just write it down and observe there's this equivalence between them. But the way we got it was through this kind of Clebsch form, as Robert said. So that's how you get them. And I'll show you that this generalizes in all sorts of interesting ways in a moment. So here P is the multiplier, as I mentioned. We maximize with respect to the U, and it recovers some, for example, interesting sort of optimal control problems on spheres and other interesting geometric objects discussed, for example, in Brocket's paper in '73 that I mentioned over there. All right, so now I'd sort of like to relate it a little bit to the discrete setting. So you can think, of course, of discrete optimal control problems. A lot of people do optimal control on the discrete side. I mean, that's certainly something you want to do if you want to do things numerically. There's an interesting history also of discrete integrable systems, going back, well, in various ways, for example, to Moser and Veselov. And this links all with this nice theory of variational integrators, for example, that I mentioned in these papers here, so Kane, Marsden, Ortiz, and West, Islis, McLaughlin, Zanna, Dislis, and so on. So there's a lot of theory about integrable variational integrators. This has a rather nice particular geometry associated with the Lie groups and the rigid body equations and so on. So firstly, I want to write down a discrete Lagrangian as opposed to the smooth sort of Lagrangian or Hamiltonian I had earlier. So this is a map from Q cross Q to R in this case. So I've replaced the velocity phase space TQ by Q cross Q, and note, coincidentally or not, and it's not really coincidentally, that here again we have Q cross Q. So remember in the symmetric rigid body equations, I had the flow on Q, I had Q dot equals Q cross Q, I had Q dot equals Q omega rather, and P dot equals P omega. So that symmetric form of the rigid body equations, instead of the standard form, was not on T star SON, but it was on a product of the Lie group, and that's exactly what happens in the discrete setting. So it's replaced by Q cross Q, you have an action integral, replaced by an action sum, L du QK plus 1, and you have a discrete action principle with fixed endpoints, just like the optimal control problem. So I take the extremum over a bunch of points now. I end up with the so-called discrete Euler-Lagrange equations, which I've written down over there, and I are familiar to many of you. And you can sort of rewrite it like this. So these are the discrete rigid body equations, and I'm interested in what those look like in this geometrical setting. So first let me relate it to the Moser-Veselov equations. So a lot of the impetus for this research, I think, originally was this famous paper of Moser and Veselov, where they were looking at a discrete version of the rigid body equations, and they wanted to see if it was integrable or not. So again, you replace the Q by QK, some point in the group, SON. You let omega k be the discrete angular velocity at time k. You have some sort of moment of inertia map. Mk is the rigid body angular momentum at time k. And then you get these Moser-Veselov equations, which go back to this 1991 paper. And there are a number of interesting things associated with it. So first of all, omega k is given by a product of qk's. Nk also depends on q by an operator lambda, but in this case there's a minus sign rather than the plus sign that I had earlier, but it's certainly very reminiscent. And also the momentum evolves by conjugation. And that's really the same thing in a way as a bracket, because if you write down a linear bracket like L dot equals L bracket something, the solution is essentially conjugation. So it's certainly related to the smooth setting. And in this case, you can also derive these equations from a discrete variational principle. And here it is. So this is the discrete action functional, sigma trace qki and qk plus 1. And the interesting thing is you can relate these Moser-Veselov equations to the symmetric setting that I mentioned earlier, and in a way, as I said, it's more natural in the discrete setting. So this is a set of discrete rigid body equations. UK is defined like this, very similar to what I had earlier, except for this minus sign on the left. And that gives you an algorithm, if you like. So it's an algorithm for computing the dynamics of the discrete rigid body equation in the symmetric form. And it's sort of different a little bit from the Moser-Veselov equations, in some sense because it computes the q's and p's simultaneously, but essentially it's doing the same thing. And moreover, just like the smooth setting that I showed you earlier, it's equivalent to the Moser-Veselov equations by exactly the same sort of transformation that I showed you earlier. If you restrict yourself to a level set of momentum, then you can map between the PQ variables and the QM variables. And in the same way as in the smooth case, there's a nice spatial momentum which is conserved. So it behaves, so the relation between the two is in some sense very natural. And in some sense, the symmetric smooth form is more closely related, I would say, to this discrete form than the smooth regular form of the rigid body equations. So that's it. And you can sort of also do this sort of intrinsically from the optimal control point of view. So if you wanted to derive these equations from the optimal control setting, it's essentially the same thing again. You have a cost functional. You have a discrete optimal control problem, qk plus 1 equals qk uk, and you can check that the optimal solution from the discrete Pontryagin maximum principle satisfies these discrete symmetric same relation I got before, which sort of what I did by seat of the pants, so to speak. So I think so really to summarize here, you can see that there's this nice relationship between all these things, the rigid body equations, the symmetric counterpart, optimal control theory, and the discrete setting. So they're all sort of linked together, I think, in this kind of nice way. What I really want to do in the remainder of the talk is just show how this generalizes a bit and explain how you get some of these other integrable systems, sort of new and old. Any questions at this point? Yeah.
The discrete optimal control problem, you need to choose a discretization of the Lagrangian.
Right.
And does it matter which discretization that is in order to get a completely integrable discretization? I wonder.
Yes, I see what you're saying. Yeah, so that's a good point. So here, I guess we just showed it so that it looks very similar to, these smooth systems. Whether the integrability is independent of the discretization or not is an excellent question, which I don't know the answer to. So that's the question. Yeah, I don't know.
So is Q cross Q symplectic manifold for all semi-simple Lie groups?
Well, if it is, as long as you, so if you have to embed it though, right? So you take SON cross, you embed it in its Lie algebra. That's one of the strange things about this business. So the way you have to think about it, at least the way we think about it, well, there's a complicated answer to that question. Actually, it is a Poisson Lie system, but that's not what we're really using here. So there is an intrinsic symplectic form in it, but here what we're doing is we embed big SON cross SON inside little SON cross SON, and that inherits the standard sort of tangent space symplectic structure from the algebra. So you're using the algebra symplectic structure, and it certainly is true for any matrix Lie group.
That means it's sort of local in some way, because
No, it's not local. So it's local only in the following sense. So I embed it. So one has to be. So there are locality things. So you embed the group in the algebra. The algebra has a natural symplectic structure. Then you can take that symplectic structure and restrict it to the group, and the flow preserves the group structure. So it's local in that sense. And then, as I said, also, if you want to get back to the original, say, rigid body equation or whatever it is you're looking at, it's the map is only one-to-one on level sets of momentum. So there is a certain locality. Yeah. So in some sense, I mean, the representation matters here. So you can't. You can talk about it for higher dimensions, but you have to be careful, but it doesn't depend intrinsically on having a matrix Lie group, which you can embed in a reasonable matrix structure. All right, so now I want to say something about the general Clebsch optimal control problem. So how long should I talk, by the way? Is it an hour, a little less than how you normally
Yeah,
go?
maybe leave 5 minutes
Yes,
before
okay.
4 so that we
Yes.
can have some questions.
Okay, so I'll just watch the time. So I don't spend so I'll go through this fairly quickly. So, and because I want to get to the integrable system part, but so let me just say something about the general setting. So so what I did was for the rigid body, but it's part of a general thing which we call the Clebsch optimal control problem. So before we were restricted to Lie groups, and now you generalize it a little bit. You have a group that acts on a manifold Q, and that's sort of an action of the group, right? Moving you from one point to the other. And the key object in this, actually, for those of you who know mechanics, is the so-called infinitesimal generator of the action, which I call UQ. So if I take, basically let the group act on the manifold and differentiate it. All right. So it's basically the infinitesimal generator of the group action. So UQ, which the notation we choose for good reason here, is d by dt at t equals 0 of q exponent 2u, tu rather, where x is the exponential map. So that's the generator. So it just generates actions of a group on a manifold. That's all you have to think about. And it's the sort of infinitesimal version of that. And the generalization of the cost problem that we just looked at is this one here. So I give you some arbitrary Lagrangian. It's a function of u and q quite generally. And the dynamics, so you can literally think of this equation A here as q dot equals qu again. And that's the particular case where you have the group acting on itself. Here it could be more general. It's just the infinitesimal generator on some manifold. That's the dynamics. And then you have these endpoint conditions. So that's the generalization. And then you can write down, so there's a little bit of formalism here which I'm not going to worry too much about. you can write down the general equations of motion, and you get these interesting, nice geometrical Lee-Poisson equations. So for that, you need the generalization of the momentum map associated with the action. You need the so-called lift of the action to T star Q, and you can write down the solution of the equations, which just generalize the equations I wrote to you earlier, and that's what they look like quite generally. But so I want to restrict it a little bit so it looks like something reasonable. But these are just the same thing as the optimal control equations that I wrote down earlier in this general setting. These equations 7.2, and there's a natural Hamiltonian which depends on the momentum map, which essentially you can think of. So you can think of the momentum map as the Hamiltonian which generates the lead group action, basically. That's the way to think about it. And what you get is, in fact, the Euler-Poincaré equations for the control U. So these are these general equations which basically replace, you can think of these again as, if you like, the generalization of the symmetric rigid body equation. I just have a pair here. The add star action is the dual of the add action. So you can think of it as just a bracket, if you like. And J is this momentum map, and so it depends a little bit on what L looks like. And you can write it more explicitly if you do choose a representation. So if Q here is a dual vector space V star, which G acts by left representation, the momentum map recovers this expression J of dl by dA equals minus dl dA, so-called diamond A. This is a notation that Darrell Home likes, but that appears in semi-direct product theory. And again, it's just a way of pairing the Lie algebra action on itself. So the formulation doesn't matter too much, but again, you can write down the equations more explicitly in this setting. So again, you can write down an extremal version of the optimal control problem. It takes this rather nice form in the Hamiltonian setting. That's equation 7.4. And the Euler-Poincaré equations for the semi-direct product give you these rather explicit equations that I've shown you at the bottom here. So it turns out to be quite explicit. And these are the so-called Lie-Poisson equations, as opposed to the Euler-Lagrange. So you can sort of write it on the Hamiltonian side, the Lagrangian side, and they have this rather elegant form, which, as I say, just reduces to the rigid body equations in the setting that I've shown you. And so there are a number of other interesting things you can do geometrically that I won't worry too much about it here, but one of the things you can do is you can restrict it to the G orbits. So this way we've looked at minimization of the problem on the whole manifold. In fact, it's possible to make it easier by just looking at the so-called G orbit itself. So I take the manifold, I let the group act on a point on the manifold, that gives me an orbit. I can directly put the optimal control problem on the orbit as opposed to the whole manifold. And again, the same formalism comes through, but you can sort of simplify things. And one of the nice ways you can simplify things, as I mentioned earlier, is by choosing a suitable metric on a Riemannian space. So if you have an orbit, there's a natural Riemannian metric on the orbit, which is called the normal metric, actually, normally. And again, if you do that, you can get a very nice particular form for the equations. So let me just show you those. So that's just formalism, doesn't matter too much. Let me just write down the formula, which I think I'll just skip that for interest of time. Yeah, so these are equations that you get in a specific case, and in this case there's a very specific form for the Hamiltonian. It's just a kinetic energy plus a potential energy, and the equations take a particularly nice form, which again reduces to various models that we know in specific settings. So I'll show you. Yeah.
Sorry if I haven't
Yes.
stood up, but
Yeah.
to which, how do you know to which level set you actually need to restrict? I mean,
Yeah.
you need to solve your optimal control problem with
Right.
the whole manifold, right? Not restrict it to a level
Right.
set.
Well, in this case, what you can do, since if you have the action of the group on the manifold, if you simply take the group orbit, you can show just from general principles that the optimal control problem on the full manifold gives you the same result as doing the optimal control problem on the group orbit, as long as you
So I
restrict
just
yourself.
can take any group orbit.
Yes, any group orbit.
Any group orbit.
Any group
okay.
orbit, that's right. So you can think of it as for example, the adjoint action of the group, or whatever particular group action you're looking at. And if you choose a nice action, then you get a particularly nice problem. So in particular, for example, the adjoint action. Okay. So this is a particular case where you can just reduce it to what we had earlier. You just take the kinetic energy, you reformulate it as an optimal control problem for the infinitesimal group action. So this is basically essentially what we had earlier. The cost function is just the norm of this infinitesimal group action, and then you get again a particular nice form both for the Hamiltonian and the dynamics. So this is what the Hamiltonian looks like in that setting. These are the functional derivatives, and you can write down the equations. Well, in this case, they basically correspond to exactly what we had earlier for the rigid body equations. So it's actually quite general, but in order to get something nice, you need to take very specific cases. And what I want to do is show you how some of these interesting specific cases, show you what they look like, show you what sort of integral dynamics arises, and I want to relate them to some of these other classical integrable systems that I mentioned earlier. So I want to start off with the Stiefel manifolds. So those are sort of fun things to think about. So for the rigid body equation, remember that the rigid body equation evolves on n by n matrices. You can think of it that way, right? So you're either looking at matrices in the group, SON, which is an n by n orthogonal matrix, or you're looking at matrices in the algebra, right? N by n skew symmetric matrices. So an actual generalization you might think about is Stiefel manifolds, which basically are non-square matrices. And that's a beautiful set of matrices which occur in various places in geometry. And this generalizes a couple of things. In particular, if you take the case, the Stiefel manifold, say with n equals 1, say 1, if you think of vectors, and I'll show you this in a moment, the optimal control problem gives you the geodesic flow on the sphere, which is an integrable system which you might have solved doing a mechanics course. And on the other hand, if you go to the square case, you recover again the rigid body. And the interesting thing that we discovered here, and I think, as far as I know this was not known before, is that you get all these other interesting systems in between on these non-square matrices. They also turn out to be integrable, and they have a nice form as well. So let me start with those. So this is just a special case of the Clebsch problem, if you like, but it has these interesting special cases, again, which we've seen. So here is the Stiefel manifold. So I'll call it a little Vn of Rn. So it's the set of orthonormal n frames in Rn. So it's an ordered set of n orthonormal vectors, really. And there are various ways of thinking about it. You can think of Vn of Rn as the set of linear isometric embeddings of R little n into R big N. And so what does the Stiefel manifold really look like? Well, if I think of matrix as n by n, that, I've called it here big N by little n, that the vector space of matrices having n rows and big N rows and little n columns. And the Stiefel manifold is exactly the set of matrices Q, where Q transpose Q is equal to the identity, but not the other way around, right? So that's the difference between the orthonormal group, right, would be just n by n, where the big N is equal to the little n, and Q cross Q is equal to Q transpose Q is equal to the identity. So here we just have this one, here the matrices are on square, and we have this one direction where Q transpose Q is equal to the identity. And you can write down the dimension. It's just this expression, big N times little n minus n plus 1 times n over 2. And that actually comes up again when we look at the rigid body equation. So that number is kind of interesting. And what about the tangent space of the manifold? Well, that's just, if you just differentiate that condition with a parameter, you can just check at a point Q, the tangent vectors are things of the form V transpose Q plus Q transpose V is equal to 0. And there's also a rather nice relationship, if you like, with Grassmannians. So one of the nice stories also, so Grassmannians, so what is the set of Grassmannians as opposed to Stiefel manifolds? Grassmannians is the space of, say, D planes in n space. It's just the spaces of planes. And that's also a very nice object, which has all sorts of nice integrable systems on it as well, by the way. So these are closely related. Instead of taking the actual vectors, you just look at the space they span, and you end up with the Grassmannian. So those are also interesting. So now let's look at some of the dynamics on the Stiefel manifolds. So again, I want to do exactly the same thing that I did earlier. I just want to take this Clebsch optimal control problem and do the same thing that I did earlier, except with Stiefel manifolds instead of, say, SON. So we consider the right SON action on the space of Stiefel manifolds, and I write down its infinitesimal generator, because remember that was the general Clebsch problem. So the infinitesimal generator is just, in this case, q dot equals minus uq. Minus comes from the right action. I minimize some L, and I have the boundary conditions. So again, infinitesimal action is constrained to A, and B here is just the boundary conditions. I can identify a little SON star with itself, just using the traces I did earlier. And I can check that this, the bundle momentum map that I showed you earlier in the general Clebsch problem just turns out to be this object. So it's Q transpose P minus P transpose Q. So that object that sort of came out of the optimal control problem, if you like, or that I manufactured when I wrote down the rigid body equations, is exactly the momentum map for this action. This is how it works in general. So it has this very nice particular form that's familiar. And then I do exactly the same sort of thing I did earlier. I just take the Hamiltonian, I minimize it with respect to U, and I look at the equations I get. So to minimize it, I'm just minimizing it with respect to L. And I can see that dl by du is this expression, q transpose p minus p transpose q. I substitute it back into the equations again, and these are the equations I get. So you can see that what's happened, and perhaps this is not surprising, it looks pretty much like the rigid body equations. I have uq and up, but I just have this extra piece L, which comes from the left, because I've sort of broken the symmetry in some sense. You know, before I had square matrices, now I have these non-square matrices. I have the action of the group on the manifold instead of the action of the group on itself. So it's just a little more complicated, but not too much bad happens. I just end up with this thing. So it's not quite symmetric, but it's close, all right? As I said, U is given above, and it's just the solution to this Euler-Poincare equation that I've given here, 8.5. So you need to compute the U and substitute in those equations, and that gives you the full dynamics.
How have you handled the boundary conditions? So you had some boundary conditions
Yeah.
for the cubes, right?
Right.
Have you lifted them somehow into the into Clebsch variables? Or?
Yeah. So you have basically. I mean, it's so in this case the q's and the p's. So the boundary conditions q of 0 and q of p, which basically in this case you just rewrite in the Clebsch variables. Yeah.
So but there's a choice, right?
Yeah, so that's true. So you have to make that choice. Yeah, if you're writing it down directly in the
But it doesn't matter if it's...
No, it doesn't matter, right? Because it mods out, right? Any choice will mod out in the end. So yeah, so that's the general Stiefel manifold, and as I said, you can think of the Stiefel manifold as being this little n by big N thing, but you can restrict it back to the problems we already know, for example, the n-dimensional rigid body. So if I just take the case where it's n by n, I get, again, L of u is equal to half uj of u, and in this case, we get exactly the rigid body equations that we got earlier. So m is just j of u here, dl by dq, in this case, becomes 0, that's that extra term, and I end up with these equations, so I recover exactly the rigid body equations as a special case, which of course I should, but at least it's nice to know that happens. And let me just say a little bit about the integrability, because I want to say more about the integrability of the system as I go along. So the rigid body equation is a rather marvelous thing, and it's integrable. And this originally goes back, as I mentioned earlier, to some work of Manikov and Meshenko and Fomenko a little bit later on. And the key observation here is you want to write the rigid body equation as a lax pair with parameter. And again, this is a wonderful computation. So I just rewrite the equation. So remember the rigid body equation is m dot equals m bracket omega, or m bracket u as I've written here. But now I just enlarge it by adding in a parameter. So I have m plus lambda lambda squared. But remember m is equal to omega lambda plus lambda omega. And bracketed with u plus lambda omega. And this was an observation of Manikov, and it's a wonderful observation. And again, it's a great computation. So if you just write out the bracket here, you see the first term, of course, if you just ignore, so lambda is a constant, right? That's the moment of inertia. So if I just ignore the remaining bits, on the left-hand side, since lambda is a constant, I get m dot. And then the first term of that bracket, there are 4 terms, right? When I take the bracket with 2 terms each, so I get m bracket u. So that's just the rigid body equations. The last 2 things commute, since lambda squared is diagonal, it commutes with lambda. And if you just do a little computation, you can check that lambda squared bracket u, the inner bracket, plus m bracket lambda, is identically 0. So that's a computation. And it's really very simple. But the nice thing is this equation is exactly equivalent to the original rigid body equation. So does everybody see what I mean? Yeah. So to that, and why does that matter? Well, you need a bunch of integrals. So remember, for an n-dimensional, or at least a 2 n-dimensional system, you basically need n integrals of motion. And in this case, this gives you exactly the right number of integrals. And the way you get them is you take the traces of the powers of m plus lambda squared. So, and that gives you various polynomials in m and lambda squared. So I get things like trace m lambda squared, trace lambda squared, m lambda squared, and so on ad infinitum. And it turns out that you get exactly, I mean, of course, there can't be infinitely many independent ones, but it turns out that they're exactly the right number. And in this case, the phase space, rather than, like I mentioned earlier, is just an orbit of the group. It's an adjoint orbit. And an adjoint orbit of a group has a particular dimension. In this case, it's n times n minus 1 over 2, minus the integer part of n over 2, which is similar to that number that I showed you earlier. And it turns out that the number of integrals that you get, in this case, is exactly half that dimension. So it's a rather miraculous thing that out of this, you get exactly the right number of integrals. I think no one really still, to this day, understands that. It's kind of a miracle, maybe not. But anyway, you get exactly the right number of integrals. And not only that, it's the right number, they commute with each other, the system is integral in a beautiful way. And there's another whole story associated with this, that it's, there's a sort of theory that this is actually why integrable systems became so popular back in the, I guess, the early 80s. People realized there was a very nice connection with algebraic geometry. You can write down an algebraic curve associated with this thing, which is just the level sets of the integrals. For example, if I take m plus lambda squared minus mu I, and I look at that as a Riemann surface, it turns out that the flow linearizes on what's called the Jacobi variety of that Riemann surface. So there's a whole sort of algebraic geometry associated with it, which actually gives you the explicit computation. So there's a very nice story, and there's lots of interesting geometry with it, some of which is in this early paper by Toda. What happened there? It just wants to log me out, or did it?
It's just you lost power.
Oh.
You can finish up your visits now, Tony.
Yes, I know, so I'm just about done anyway, so.
Your caps
See if I can remember my password.
Your caps lock is on.
What's that?
Your caps
Oh,
lock.
caps lock is on. Oh, thanks. How did you see that?
Oh,
Oh, show that there. Thank you. All right, let's try this again. Oh, there it is. Okay. Yes, I know I should finish off. So yeah, just get 2 more minutes. So that's sort of the story. So it's captured a lot. So let me say, yeah. So this is I'll just flash up a couple of other things in the remaining couple of minutes. So again, you can capture the symmetric representation of the rigid body. It's a special case of this, which is also integrable. And by the way, you can think of it, the story of how that's integrable, and of course it has to be, is also kind of interesting. That's in one of these papers. I don't want to say too much. Let me just sort of end, though. So this is something that we're looking at right now. So hopefully there'll be another paper on this. But if I take, there's a very special case, and this relates to the work of Moser. So there's the so-called rank 2 rigid body. So this occurred in this famous paper of Moser on integrable systems and geometry of quadrics. So it turns out you can write this, so instead of doing the matrix case, and again, there's sort of various things you can fiddle around with, you take the vector case. So instead of having the matrix big Q I have here, I just put a little vector Q, a little vector P, and I have the same sort of picture. So now U is acting on Q, the vector big U is acting on P, and so on. And then I can rewrite the equations again as a lattice pair, just like the manifold thing. So I have L and B. And this sort of formulation here that appears exactly in Moser's original paper actually. So this is called a rank 2 perturbation, because it's a rank 2 perturbation of lambda squared. And it turns out that this system is integrable in a rather simpler way. So instead of the rigid body where I have n times n minus 1 over 2 and so on, integrals, this is just n by n. So it's an n by n system. I just need n integrals. And you can capture the n integrals just by looking at the traces of the powers of n. That's all you need, right? Because, you know, if you think of a matrix M, it has n eigenvalues. The traces of m capture the eigenvalues. That's enough to integrate the system. And this is what the momentum map looks like in this case. And the nice thing also is that there are many other systems that fall into this general picture. For example, the geodesic flow on the ellipsoid. There's the Neumann problem of a free particle moving under a momentum map, and so on. So this captures a whole lot of integrable systems, which you can also write in a symmetric form. You can show they're integrable, and you can capture them in a rather nice lattice pair form. And then I could have, you know, if I had more time, I would have gone on to discuss again the system that we looked at with Aria on symmetric matrices in Toda, but it turns out to fit into that picture as well. But I think this is a
So
good
this is
place to stop.
exactly the free rigid body.
Yeah, this is exactly the free rigid body, except on a low rank orbit. Yeah. It's a low rank. Yeah, but again, it preserves the rank of the orbit, and it has this nice, simple structure. All right, thank you very much.
Thank you, Tony. We do have some time for questions. Robert?
Well, you said the integrability of the free rigid body is simple, but
Well, no, I don't claim it's simple.
well, with the Manifold version,
maybe
but
that's-
certainly for the Moser top, it's not at all simple, right?
No,
it's
I'm-
unbelievably complicated.
No,
So
no, I don't claim it's
what's going
simple.
on there?
What I was saying is, I'm not even claiming the rigid body, the smooth case is simple. I'm just saying the n by the low rank case is simple. It's simply in the sense, it's not that simple either. I think there's really cool geometry associated with it. So the only way it's simple, as I'd say, is that there is a 2n-dimensional space, and you know what the integrals are. They're just the traces of m.
So
In the general case, you need that lattice pair with parameter. There are all sorts of crazy integrals. But in fact, this is something we worked on. It's actually even this itself is very complicated, because the way these low-rank orbits sit inside the orbit of the big system is not obvious. And in fact, I don't think Moser understood them, and we still don't understand them. So we're struggling with that.
Looked at the rank 2 Moser top then.
So we've looked at exactly. We've tried to look at a whole lot. Well, actually, the Moser Veselov.
Yeah, discrete top.
Oh, that's a good point. So we've looked at it in the subsymmetrical. We haven't really looked at the Moser Veselov. That's actually a good suggestion. Is that known, or let me just think? Do I know? I think some of it might appear in Dynft. Anyway, we're trying to look at various. So we've got these various rank 2 things. At the moment, we're just looking at the smooth case. I need to think more about the Moser Veselov top. I think one can do it using loop groups or something. But anyway, that's a good question. Yeah.
All right.
So this Clebsch optimal control problem looks a lot to me like a special case of Lagrangian mechanics on Lie algebroids.
Yeah, there is a way of doing that actually. I had a slide on that originally, which I deleted. But yeah, no good reason. But yeah, it does. You can formulate it so like that. Yeah.
Does that
Yeah.
point of view tie in
Yeah.
to integrability in any way that lends insight to it?
Not that I know of. I mean, it's a nice way of thinking about it. But yeah, you can absolutely think about it that way. Yeah.
All right. Let's thank the speaker once again.
All right. Thank you.